So let's start our lecture today. Um, uh, so uh, I'm checking what I left with. I think there's some point where I think I left with some ambiguity in the middle. Um, I think originally I split the region into 8 parts, I think. So I think this is the line y equal to x, and then this is the line y equal to negative x. And I think I named each region 1 through 8. Let me try to recall. Yeah, I think I do not have this one. So, where is it? Okay. So, so I can vaguely recall that I think there is like 1, 2, 3, 4, 5, 6, 7, and 8. And there are some points that after rotation it becomes lies in the other sector. So, for example, and so basically, if you have a point, so let's say omega be a point in 1, then this implies that if you take so omega, which is equal to let's say r into the I theta, where it lies in the first region. So so what I want to do is that so I want to calculate what is 1 over omega squared. So which is equal to first I get 1 over r squared, and then I get e to the, so first I square it, it becomes this one squared, which is equal to e to the 2 I theta, I2 theta, and then I take the inverse, which is negative 2 I2 theta. So if I theta and multiply it, it lies in the fourth quadrant. And then so so similarly, So similarly, I have, so if so let's say this is omega 1, and then so if omega 2, let's say that's in the second quadrant, so so this is equal to, let's use the same letter, and then so this implies that 1 over omega 1 squared, which is equal to, so basically I square it, so it lies in the third quadrant. So for 3, it goes to, so I square it, it should lies in the second quadrant, and then for 4, I think it should lies in the first quadrant. Yes. So these lattices, they are exactly spanned by, I think that may be caused by they have different patterns. Because I think even though after some rotation, they lies sort of. So what did I calculate? So so. So I'm calculating region 2 and region 8. So let's see. So for region 5, it goes to. So first I square this one, and then double. And then here, same thing, I square. So it also lies in the region 4. And then for the region 6, so it should be so yeah, so it should correspond to the region 3. And then for the 7, because it follows consecutively, like the previous pattern. So, and then for the region, because think of like for each region you increase like by like a 2 pi, so then the total rotational increase is like 90 degrees compared to the previous one, and then do the symmetry. And then for here, basically if you double the angle like here, basically is the same thing as, because this is our pi, and if you double, then this part becomes like 360 degrees. So it's just this part, this angle here, and this angle here corresponds to points here. So after the doubling angle effect should be the same as the region 1. So and so on and so forth. So then I think we should give so 7, it should be mapped to the same thing as 3, and 8, so it should be mapped to the first quadrant. and then so I'm comparing the so I'm comparing the second one with the eighth one. So, however, I think the reason why they are different is, so for example, if you have a lattices that looks like, for example, let's just think of a simple example where I think I assumed in the past that this omega 1, they are just real, and but yeah, so we also on the same assumption. And then this omega 2 is on the imaginary line, but they may not be the same. Let's just assume that the modulus, so let's say that it is plus, and then the modulus of omega 1 is bigger than the modulus of omega 2. So here, if I'm looking at the lattices that's in this 8, so I think maybe after rotation they lies in the first quadrant. So yes, and then so basically you can think of this one as so this is like this point, but sort of missing this angle here, and then if you doubling the angle, it will miss, like, because it's 660 minus this one, and then if you multiply by doubling this one, it will be twice, like 720, but minus 2 copies of this one, so it will sort of less here. And if you do a symmetry, it will be like somewhere here, and then like somewhere here with this angle like 2 theta or something. So suppose that this is like suppose this angle theta. So this angle is maybe 2 theta. I mean the absolute value. So and here, but so this lies in the first quadrant. But however, when you start with a point that lies in the second quadrant, I think the thing that you may went wrong is that, so now I think the ratio doesn't match, I think. So because, so here if you like keep increasing and increasing, then finally there is a point that lies on the region 2. So however, this may not be the same pattern as this theta. Like, so here this is, roughly speaking, this is like it has a length like omega 2 or omega 1. So it has the side length where the adjacent, so points, let's say points in region 8. So roughly speaking, okay, so it has adjacent to be the omega 1, and then the opposite to be omega 2. Yeah. So I should be more careful. So so roughly speaking, because so I mean I have to take care of the absolute value, the modulus, and also, but the adjacent is that. So at least like when I for each point I pick an angle, right? So the adjacent is like the copies of omega 1s, and then the opposite is like the copies of omega 2s. However, when I pick a point, let's say here, then, so I think it depends on how I look at these points, right? So, so if I pick a point, so which angle am I interested in? So, wait. if I look at the same, site, so if I look at, let's say, in the same view, so namely, so here I start to count the angle like in the negative order, and then I make it positive. But yeah, but you know what I'm saying. So, and then however here, if we count the angle in the regular positive way, so then the adjacent, wait. Yeah. So the adjacent is exactly the. Wait, I don't think I can do that, right? I don't think I can say just use the real angle theta. Like, I mean, these angles is like some negative angle. So, let's say, so let's just say, so let's say that, because what I'm thinking is just think of this rectangle, right? So think of this rectangle. So this is the angle theta. But I think there should be like a sign associated to this angle. Otherwise, the direction will be messed up, right? Because when you when you multiply it by 2, I think because when you multiply by 2, this theta goes this way, but this theta goes that way. So there is like very essential difference between this theta and this theta. So so let's call this maybe theta minus. Let's call this theta minus, indicating that it counts towards the negative. Because when I double this one, this theta, it goes in the other direction. And then this is the theta positive, this is the original theta. And then, so for this guy, so what I have is that I am having, so here, I think this is also some sort of similarity because so for this angle, namely, I think at least from the name, I can sort of tell that the adjacent is like this omega 1, right? So so let me add one words, and together with and the angle is counts towards the negative direction, and then so points, let's say in this region 2, and then what we have is that that's in the region 3. I think there is a portion mismatch. If I count this angle in this way, then so what do I want to say? So I want to say they eventually cancel out, but they didn't, I think. But somehow they didn't cancel out because I think eventually the conclusion I get is that they correspond to a full lattice or something that counts over the whole plane. So I think that might be the issue here. So they may contribute to the whole lattice. Why? Because here, so over this region, some ratios are missed, right? So what is the ratio they missed here? So the ratio they missed is exactly the ratio that, so if you fix omega 1, right? And then if you go in this direction, and then if you cannot go too far, right? So if you go too far, then so if you fix one omega 1, then you can't have too many omega 2 being added, or being like being added. Yeah, let me just frame it here. Otherwise, it will go off the end, right? So otherwise, it will go off. So otherwise, it will go off. Otherwise, it would go off the region, right? Okay. And then, so however, in 2, right? In 2, I cannot be too small. Otherwise, it won't lie inside the region. Okay. So however, point in 2, so same thing. So, and let me just say that the angle is theta plus. And then, if you fix like omega 1, then you can't have too little omega 2, so otherwise you won't reach the region. You won't reach this 2. Okay. So how can I see in picture that they contribute? Yeah, I think wait. I think there's another question. So this might not be right, I think, because they lie in the opposite region, right? So one lies in the lattice in the 3rd quadrant, one lies in the 1st quadrant. So how can so why am I getting these full sums? Okay. So let me think of it in this way. So so I have to think of the scales. Right, I have to think very precise in this way. So let me think of it in this way. So okay. I think one question becomes, if I really doubling, okay. So if I double this one, right? So I think there is some quantity that I can follow here. So basically, I know that this angle is like 1 unit of theta. So suppose that I fix omega 1. Okay. So if I fix omega 1, then I'm letting so let me do this. So let's define the unit to be let's use this omega 2 to sort of count, like use a unit, like a measure, like for that's measuring this angle here. So let theta k to be the angle where to be the angle where you have this omega 1, and then this it is k omega 2 rectangle. Yeah, so let me say maybe it's like the arctan of k modulus omega 2 over modulus omega 1. So so then if you double it, right? So basically you are just multiplying this theta k. So so here if I double this theta k, so for example, so for k large, right? So I have to find a k where the this omega 2, the copies of omega, the k times omega 2 is bigger than omega 1, right? So that k naught to be the smallest amount of to be the minimum of to be the minimum amount. So I know that, so this angle, so let's forget about the 2 theta here. So so this angle, so I'm counting from here, so this angle is exactly the theta k naught. Okay, so this is theta k naught. Theta k naught. Okay, so maybe it's a little bit small. Can it be seen? Oh, it's hardly see. Okay. Yeah. So this is theta k naught here. Okay. Then so so when I double it, this angle is exactly 2 times theta k naught, right? So let me just erase this part. Maybe let me erase up to here, and then so the quantity that I'm interested here is that so then I have 2 theta k naught here. So I'm doubling this angle, and then what I do is that I'm make a negation to this one. So this is the one quantity that I'm interested in here. And then for the points, so for this point, so what do I do here? So basically, I'm taking. Oh, okay. So this is not only just k naught, right? So it is all the. It could be all the k such that this k bigger than or equal to this k naught, right? So yeah, so maybe yeah, so our k or k for so let's say angles angles in the chain 2. So yeah, so angles in 1/2 squared. So the chain 2. So for the angles into outer change, and then for where for k it should be bigger than or equal to this k naught, and then fixing omega 1. And then let's focus on the let's focus on the let's focus on the so points in 8. So points in 8. So what I have is that okay, so I have is should be 2 times so 2 times so I think it should be because it should start with the negative, right? Yeah. So let's start with the negative theta k. So negative 2 theta k. So yeah, in this case, I'm using the theta k as the positive angle. So in this case, this theta k is always positive, which is always positive. So here, in order to denote the position for this point, I'm using the negative angle to denote that it is really like lies underneath the x-axis. So so negative 2. So this is where I multiply this one, and then I will do a negation. So this becomes positive 2 theta k for so for k should be less than k naught. So So yeah, let me check the time here. Okay. So yeah. So sorry, I'm running out of time. So yeah, let me I guess stop here today, and I'll continue next time.